Okay, welcome to another Kent seminar series this week. This week we have Devakantra Mishra, who's a postdoctoral researcher here at the University of Illinois. He's currently working on a rail project related to settlement. That's what he'll talk about today. And he has been here since 2006, where he's finished his PhD last year. Before that, he was at Texas Tech for a master's, and then before that, IIT Kanpur in India. And he works at Professor Tutumler's group on unbound material characterization, testing, and today I believe he's going to talk a lot about instrumentation relative to this bridge settlement project they have from, is that FRA?
Yeah.
FRA. Before we proceed with Deb's presentation, next week is Peggy Curran. She'll talk about technical writing, so everyone should attend for that. That should be mandatory, probably, right? Second, 2 weeks from now, Brian Hill, and then we have a break for Thanksgiving, and then after Thanksgiving, Peggy Curran talks again about some more technical writing and issues. We can't cover it all in one series, so let's welcome Deb this morning.
Thank you, Professor Eisler. Good afternoon, everyone. I'm Deb Mishra, and I'm going to present some work that we have been doing over the last 1 year for a FRA-sponsored project. The title of my presentation is Investigation of Differential Movement at Bridge Approaches Through Geotechnical Instrumentation. First of all, this presentation is based on the work we have been doing under this FRA-sponsored research study that started in October of 2011. The PI is Professor Tutumler, the co-PI is Professor Tim Stark, and I am the research engineer officially, and Dr. James Hyslip from High Ground Engineering, he works on this project as a visiting research scholar, and graduate student Steve Wilk just joined us this semester, and he'll be working on some of the flak modeling work that we are going to do in this project, but that modeling is not part of this presentation. So first of all, acknowledgement to the co-PIs, PI and co-PI, and also Dr. Hyslip. So also this project is, we have several research partners and railroad industry partners. We work closely with Amtrak and Union Pacific, and there is some potential for some instrumentation at one of the NS sites. If time permits, I'll talk about that a little bit. And then we also have industry research partners, which is GeoPeer, Tensar, and Nicholson, and this is for different remedial measures that we want to propose, like selectively which one suits which site based on our instrumentation work. First of all, acknowledgements from FRA, Mr. Cam Stewart, who is the project supervisor, Dr. Ted Sussman from Volpe, who is the technical supervisor, and Mr. Hugh Thompson from Amtrak. My presentation today is primarily on some Amtrak instrumentation we conducted over the summer. So Mr. Mike Thomas, Marty Perkins, Carl Walker, Dr. Steve Christmer, Dave Staplin, Mike Trocino, they helped us get access to the sites, and with all the instrumentation, we were actually learning from their experience also as we go about railroad instrumentation. Then Union Pacific, Dwight Clark, John Jerome, UFI, James Ford, Hassan Kazmi, and Mike Wenek, they were with me in Philadelphia this summer. I'll talk about what instrumentation we did. And finally, from High Ground Engineering, Mike Lavallee, who is basically Dr. Hyslip's colleague who has done a lot of the geometry analysis for us. Quick outline, I'll establish the background of the problem, then how we selected the transitions, then I go into the instrumentation and show you some pictures and details of what we did in terms of the instrumentation. I'll show some analysis of the acquired data. I call it preliminary because we have, this is a lot of data, and there's a lot of scope for different kind of analyzing and establishing different trends and finding out what's going on, and then quickly talk about a little bit of future research tasks, and then we'll wrap up. Background. So bump at the end of the bridge. This is something that is very commonly known, at least for pavement engineering. It has been extensively studied, and what all you see is everybody who has driven or been in a car knows that as we hit a bridge, even if we don't see it, we always feel it, because there is always differential movement between the bridge approach and the structure. So for the pavement, you can clearly see that there's a lot of studies that have been conducted, and one of the most extensive ones is the 1997 NCHRP synthesis by Professor John Louis Brio out of Texas A&M, and who prepared the synthesis. And you can actually see that it's about 100 million per year spent in the US towards mitigating highway bridge approach problems. It's a very well recognized problems and studied extensively. Actually, the project co-PI, Professor Tim Stark, he actually conducted an extensive study on the same problem for the IDOT, and actually there is a report available in public domain, as well as he published a TRB paper based on that. Then similar is the concept for railroad track transitions or bridge approaches. Now, what I'm talking about here, the instrumentation we talk about in this project is primarily bridge approaches, but you can imagine this as a track transition. What is a track transition? A point where the properties or the characteristics of the track suddenly change from one aspect to the other, basically. So you can imagine grade crossings, you can imagine tunnels, you can imagine culverts. All of them actually represent track transition problems. So when this project got started, we actually started with the broad aspect of track transitions, so studying maybe different type of transitions. But then when we conducted a survey of different railroads, our research partners, to look for sites that we can instrument, they all said that bridge approaches are the primary transitions that they have problems. So basically it kind of ended up becoming a bridge approach, which should essentially represent all types of transitions. This is a PhD study out of, these figures are a PhD study out of Texas A&M, Jennifer Nix, and she actually showed how you can actually have a bump immediately. This is nothing but the bridge not moving, but the approach slab immediately to it, the approach moving, whereas otherwise you can actually have a dip somewhere. It's not really a bump, so you actually go down and then come up, and this is when I will show you some track geometry data. The belief and the analysis results show that it can actually be some dynamic aspects. Like imagine a train actually moving off the bridge and getting onto the approach. So there is a level difference, so it actually jumps onto that. But as you know, this is a mass, like a spring mass kind of system. So all the dynamic forces or the inertial forces are not being applied immediately. So after some time, it actually generates the peak in terms of the dynamic force. So that dip actually can be a little bit further from the immediate approach. That is what I'll show you from some of the geometric analysis. Approximately 200 million spent annually on track transition maintenance. This is a 2005 data, and before that in 1999 also 100 million per year in Europe. There was a statistic reported there. And what you can also imagine is this bump at the end of the bridge becomes very important when you have high-speed traffic. You have now in the US we are talking about increasing speeds constantly, and then when the high-speed trains come, this kind of an bump or differential movement can actually result in significant dynamic loads being applied on the bridges, or and lead to bridge damage, passenger discomfort, or damage to rail and car components. What are the possible mechanisms? There are some studies that have actually either done some kind of numerical work on customized, like rail-specific programs, and then characterize the stiffness of the layers and seen that. I mean, it's obvious to realize that as you go from the track, the approach track to the bridge, the track stiffness is changing, because you're going from something that is standing on just like subgrade or embankment fill to something that is on deep foundations. Then you have discrepancies in track damping properties, like how much of the dynamic characteristics or dynamic effects can be absorbed by the approach embankment versus what is going on the bridge. Then there is different factors. You can say track modulus differences, quality of approach fill, how the approach fill is depending on how long it has been sustaining loads. It may undergo some settlement, impact loads, ballast material. There may be a lot of movement within the ballast, and as you know, one of the common ways of resurfacing track is just by tamping. So by tamping, you are raising the track surface. Now what happens after that? I mean, is it going to settle very fast? Inadequate drainage, then you can have traffic quality of construction all coming. Like quality of construction comes into picture, like if you're compacting the fill or if you're doing the track stabilization with the vibratory like the vibration system that is used to do track stabilization, if they do not go sufficiently close to the bridge because of equipment considerations, you don't want to have the bridge vibrate in a resonant frequency or something. So if they don't go sufficiently close, then you may have higher settlement at the approach right next to the bridge. So this is how the objective of this project is development of design and repair techniques to mitigate and minimize and mitigate differential movement. So we are considering new track construction as well as rehabilitation measures, because a lot of the track that is there, they see recurrent problems, so you have to come up with some rehabilitation techniques. It cannot just be new construction. 36 months project. First task is to monitor. Second is to identify from monitoring what layers are contributing, what layers are settling by how much, and what factors are contributing, and depending on that, take different scenarios for those given bridge or transition geometries, implement them through modeling, and then see what are the remedial measures. Like try different remedial measures first through modeling, and then whatever you think is working, discuss with our railroad research partners and consider implementation of some of that in the real sites. Track transition selected for instrumentation. First of all, so far we actually have worked with Amtrak and UP to select track transitions. At Amtrak, we actually instrumented over the summer the Northeast Corridor, which is basically in the northeast part that is very heavily used Amtrak, actually relatively high speed trains. The highest speed trains in the US actually run in that part. The part that we instrumented was actually as high as 110 miles per hour, but as you go up to New England, you can actually hit about 150 miles per hour. That is the train speed, so speeds over there. 2 bridges we started by, and then we instrumented 3 bridges. I'll show you what we did. And then Union Pacific, there actually, as some of you may know, that reconstruction and upgrading of tracks from Dwight, Illinois to St. Louis, Missouri, they're doing that. This is the Illinois high-speed rail project, and there are some bridges that they are going to construct new, basically some bridges that are additional tracks they are going to construct. So it actually presents us a different scenario. Like Amtrak Northeast Corridor, it existing tracks, very frequently used, so the settlement mechanisms may be different versus what we are like new reconstructing and experiencing this heavy freight traffic. The Northeast Corridor, where we instrumented in Chester, Pennsylvania, it is approximately 10 to 15 miles south of Philadelphia, and 4 tracks. There are they're numbered 1, 2, 3, 4. 1 and 4 are primarily for freight traffic. They do not carry the high-speed train. Remember, the definition of high speed is different in this country than somewhere else in the world. I'm talking about the highest speed here, like 110 miles per hour. 1 and 4 do not primarily carry that. That is 2 and 3 that carry. And track 2 is primarily northbound. Track 3 is primarily southbound. And as I said, speed of operation is 110. And analysis of geometric data focused on both track 2 and track 3. So we wanted to primarily focus on the Acela Express and the high-speed trains of Amtrak that are running in that corridor, because we have Union Pacific where we can actually get the study the behavior under freight trains primarily. So we wanted to get the high-speed trains there, and we also did GPR scanning of the bridge approaches that we selected in June. And I'll see you some of the results, and 3 bridge approaches were finally selected. This is how we started basically. So this is the Chester area, and we worked with Dr. Steve Chrismer of Amtrak, and actually John Winnick also helped with some of these preliminary data analysis. And what I'm showing here is 2 bridges, Madison and Hinkson. So this is Hinkson, this is Madison, and these are basically 2 runs of the track geometry car train. And it is collecting the data, and this is profile error. You can just think of it as a surface curve basically, okay, like where it is lying in the space basically. And what you see is there is a bridge here. Do not worry about why the 2 lines are different here. There was actually some mismatch in the data initially. I'll show you how it was actually corrected later. But what I want to show is if this is the bridge, you actually see that there is about, like, this is 4300 and this is about say 4,500, so maybe 200 feet or something, and you can actually have a dip of about 1.5 inches, which can be very, very significant if you are going at 110 miles per hour. The same is true for Madison, and there are actually so many, like the 12.85, which is actually the Hinkson, it was surfaced 4 times since 2009, but 13.25 actually 7 times since 2009. So it is recurrent, it goes again and again. I'm going to show you quickly a video, and this video is actually taken not at one of these bridges, but just a couple of bridges away, very close. And what I want you to focus on is the ties over here, and I'll actually play this video twice. This is a train moving, and you can actually see the focus on the 2 slippers, the 2 ties somewhere here, okay? And you see the movement actually. This is how it is bouncing up and down. I can actually play it quickly once more if you missed it. And one thing to also focus is see how white the rail is over here. So apparently there is some tie degradation also happening, some pumping also happening from the ballast layer, some ballast degradation. So this is the area that they had recurrent differential movement problems. So then we went into, then we requested further data from Amtrak, and then it was analyzed, and this is the entire area. So see all these names, they're actually bridges. So within a stretch of like 2 miles or something, there are 15 bridges in that area that is very close to each other. Every road, street is basically an undergrade bridge. And what these plots actually show is, if you look at the colored ones, the red, the y-axis is time, okay? So it starts from January of 2005, goes till January of 2010. So this is time. And at any point, red means there is a huge or big deviation in the profile curve. Then blue, so blue means that it is relatively smooth. Green is somewhere in between. So as you go with time, the more and more red if you see, that means that the track resurfacing problems were coming back again and again. That is the bump problems. So say for example, if you take this street called Upland Street, you see it was red, they fixed it, it became blue, again came back, again something was done, again it is red, again green. So it is a recurrent process. Interestingly, if you look at Madison, that was initially the bridge that was selected, you actually see that it showed nothing. So one track geometry data actually showed us a very big dip on that, and we were thinking of doing that. But by analyzing the entire area, and by the way, this data that I'm showing is only for track 3 at this point. Okay, remember I said track 2 and track 3. We wanted to focus on both of them. So from this preliminary thing, and then if you look here, this is the space curve again. It's just where the track is lying, and you can actually correspond to, like for example, if you go to Upland, this location is actually corresponding to this kind of a dip, and then it's coming back. This is the 0 line. So Hinkson, Caldwell, and Upland and Wells, they said recurrent problem, no significant roughness at Madison. So the initial selection had to be actually rechecked. So we actually went back and did all that, and then again, this is this is a 25-foot moving window that we used, and what you see is Caldwell and Hinkson, they were showing, and Madison was not really showing a lot. So north abutment, look, so this is direction north to south. So if you actually see Caldwell and Upland Street, the north abutment is actually, this is the south abutment, this is the north abutment. You see the north was a lot more recurrent versus the south abutment as you move. So then Dr. Jim Hyslop, who is actually the visiting research scholar for this project, his company actually did GPR of this area to see if we have any underlying features that can actually affect significantly the track performance. And we had some anecdotes about some of the tracks actually potentially having asphalt, and maybe that will affect your like differential movement, but that did not really we did not really get, during the drilling also, we did not see any concrete proof of asphalt, but what we did use is from the GPR and from this, the mid-chord offset data as well as the space curve, we were able to actually go and see this is the space curve, and if you take here, we actually decided that we will place two locations. One is 15 feet and the other one is 60 feet from the north abutment, and this is the Upland Street Bridge location. Similarly, we did the exact same for Madison Street Bridge, and this is on track 2. The other one was track 3, and here we selected 10 foot and 60 foot based on the space curve, the position of the maximum dip, and somewhere like halfway in between for instrumentation. Now, remember, the approach problem may be significant when the train is entering the bridge versus when the train is exiting the bridge. So these two sites, the first two sites, were actually when the train is entering the bridge. So we also wanted to capture a location where the train is exiting the bridge. So we actually went to the Caldwell Street Bridge location, and this is 80 feet from the bridge abutment, and you see that there is a big dip here. So we actually selected that location. Development of instrumentation plan. What are the potential mechanisms? Why can the track settle at a particular location? You may have ballast movement, you may have the embankment fill move, you may have the subgrade, the native subgrade move, and also the stiffness, how the stiffnesses are changing. If we get the stiffness characteristics, then we can actually make some predictions about how it is going to behave under loading. Because remember, there can be two aspects. There can be the elastic aspect of the differential settlement, and then there can be also permanent settlement. The track can actually go down, so you can actually have bumps. So instrumentation objectives, we wanted to measure elastic as well as plastic in the embankment fill, in the ballast layer, and the vertical wheel loads, because we wanted to collect data, deflection data under train movement, and then measure what wheel loads correspond to what deflection, and that can actually give us the track modulus and stiffness values. What we did is we used something called multi-depth deflectometers. For those of you who are not familiar with this concept, what this involves is that you drill a hole and you install LVDTs essentially at different locations with depth. So the anchor, you drill the hole deep enough and assume that your bottom point, which is anchor, that is not moving. And then you put LVDTs at different locations along the track fill, and you actually use, this is a schematic actually taken from a paper, and if you see that these balls, they are actually expanded to hold on to the side tubing. So what happens is it locks up with the layer. So your anchor is constant, and then as every layer moves, because this module, the MDD module, is locking up against the layer, it is actually moving up and down. So it will actually induce your voltage. So that is what is going to give you the movements of individual layers. Now the point is, MDD is the technology came out of South Africa, and as you see, it was actually early 80s or mid 80s when it came out. It has been used a lot even in this country for pavements, but for railroad applications, it is primarily only used in South Africa, and in this country, only 2 projects have used MDDs to any extent, and out of them, one was actually Professor Ernie Sillick's study in an Amtrak bridge back in 1997, and after that nobody else has used. The other one is a very small application, and because this is very customized equipment, very specific to your installation conditions and everything, so every component of this installation we had to manufacture in our machine shop here, so, the civil engineering machine shop in Newmark. All the components that you see, and this is where Mr. Mike Thomas of Amtrak, who is actually their instrumentation specialist, he actually gave us a lot of drawings, and under his guidance we developed everything. So this is actually this picture, this is the module you see, and the interesting thing is you see the part where the rubber, it looks like a plastic rubber with small balls in it, that is the part which expands. So as you screw the top screw, the balls actually expand and hold on to the side of the hole, and that is how it locks up. And we actually designed a customized drill rig to drill on the track, and then again all the constraints come into picture because you have catenary cable on top also, you have to have enough clearance and everything, and you should be able to get onto the track and get off the track as quickly as possible, because that is, by the way, the busiest corridor in America. What we did use, and this is a little bit different than the traditional application of MDD, what we did use is something called the independent anchoring system. So the way it works is that we don't have just one anchor and every LVDT anchored to that one anchor. So in this system, every module works as the anchor for the one on top of it. So basically, if you're talking about module number 5, then it is anchored at the real anchor that I said, which is deep enough. But the core of LVDT number 4 is actually anchored to LVDT number 5. So as this layer moves, then and assume if this layer moves and this layer actually remains constant, you'll actually see voltage induced just in that one LVDT. It is not, everything is not with respect to the anchor. So in a sense, what this is the voltage that you read in any given LVDT is the deflection of that particular layer. And this is a picture of the chain, MDD chain that was being prepared in the lab. And we also did put strain gauges on the wheel, on the rail to measure the vertical wheel loads. And this, what we did use was 2 elements shear strain gauges, and they were put on the neutral axis at 45 degrees. So basically to measure the principal strains in that direction. And this is calibration of the strain gauge on the rail. I'll show you more pictures of that. What we did put is, for every approach, we put 2 MDDs. Now, each MDD had 5 LVDTs, deflection measurements at 5 positions, and 16 strain gauges to measure the vertical wheel loads and the tie reactions also. Now, instrumentation was always carried out between 1 a.m. and 4:30 a.m. So we had track clearance. After 12:30, we had to set up everything, and by 4 o'clock, we had to start carrying everything out, because around 4:35, the first high-speed train goes by. We do not have access. So it took us a month. 10th July to 3rd August, we stayed there for instrumenting 3 approaches. Drilling an MDD installation, some of the pictures. This is a tripod, and again, just imagine this is, we get track clearance. We set up this triangle, the wooden triangle, just to have a base over the rail. Then this is the tripod, and then we raise the drill rig on top of that. We mount a drill, and then we start drilling at the on the tie. Basically, it's a 1 3/4 inch diameter hole. By the way, it's like 45 millimeters. That is all the size of the hole is. We go through in the middle of the reinforcements of the tie, so that we don't cut into. This is, you can see a picture taken of the hole through the tie. It actually shows you some ballast particles, because we are somewhere between the tie and the ballast right there. The interesting thing, all you can imagine, is when you drill through ballast, it becomes very interesting, because ballast is just going to fall into the collapse into the hole. It is not going to stay out. So what we do is that we drill a hole through the tie, and we put this is similar to boating foam, like insulation foam. So what we put is, we put in there, and we put like seal the hole from top. So it actually expands down, and it actually kind of binds the ballast. So you can slowly go and chip away that position and make a hole that is clear enough, so that it doesn't fall. And then once you are clear through that, you can actually use an auger bit just to keep going down. And this is actually 2-part epoxy grout used to bind the lining tube. Now, once you have drilled all the way, and by the way, we only go by 2 to 3 inch increments, so that we can actually know where the layer interfaces are, because the idea is to instrument the layer interfaces, so that you can know which layer is settling by what amount. So this, as you can imagine, this is a very long process just to drill and we did go down by 118 inches, so 10 feet almost for every hole. And what you do is, once the hole is complete, you put a 2-part epoxy, and then you see this one here is a lining tube. And this lining tube, you can just imagine of it as a vacuum cleaner hose with the inside not ridged. The inside is plain. So you have enough room for, you have proper grip between the module and the pipe. So you just insert that using a steel pipe, and then you pull the steel pipe out, and that is what your prepared hole looks like. These are the modules. By the way, if you want to see, take a look at of any of these components, I have them all in on my desk, like below my desk. You can come and take a look at all the parts that we manufactured. And this is a module, and then this is the LVDT. So it just gets fitted into the LVDT. And you see here, like for example, on this picture, if you see, there is a, this is the bottom, like one of the lower ones, and then this is the top one. So you see the core of the top LVDT is actually held by the bottom LVDT. And then once the drill hole is complete, this is a specially designed insertion tool, which is actually provided to us by Mr. Mike Thomas, and then you can actually put this in and you can actually insert the MDDs, and because you know your exact length of the cores, because this is all prepared in the lab, so you know exactly from your drilling information where you want to put individual MDDs, you can actually zero the voltage, like you can put them in such a way that when they are at fixed distances from each other, then the voltage induced in that particular LVDT is 0. So that's the 0 position. So when you are inserting in the field, you actually have an amplifier connected to the position. So you start moving it down. Once you see the LVDT, you find the 0 position, you lock it down at that position. So that is your initial positions. Okay, and then after we finished installing, now remember what I said is that the initial settlement after you tamp the track, because you're tamping the track, it is all puffed up basically, and initially as the train passes, there is a lot of settlement that's going to happen. So we wanted to capture also that part of the settlement. So what we did is, after our drilling, we installed the bottom 3 sensors. Then we put a tamping protector, basically a steel tube in the hole, so that when they tamp, they're not going to damage the hole. And then we actually requested Amtrak, and Amtrak was kind enough to give us a tamping machine for that night, so it can actually came and tamped at that exact locations, so that we can capture all the initial settlements after tamping that is happening corresponding to each location. And this is the instrumented locations, by the way. Strain gauge installation, these are dual element strain gauges. You just need to mark the positions and then you just grind it and then spot weld it at the exact locations. Calibration, what basically is, as you can see, whether you assume the rail to be a free simply supported beam or a continuously supported beam, all that changes how strain is going to be induced, and you don't know, it changes from site to site and everything. So what is important to do is have a calibration frame, and actually after you install, you actually calibrate the strain gauges on the rail. So you have a load cell on this calibration frame, so you apply the load directly on top of the strain gauges. So you read the load from the load cell, and then you read the load that your strain gauges installed on the rail are shooting out. So basically you know that if my rail is reading this many millivolts, that is actually how many kilonewtons I'm applying. So you can just use that I'm going to skip through this because this is going to be this is the different positions of the MDDs. You'll actually see it. We also did top of rail measurement through surveying, so that before and after tamping, we actually found that as you tamp the locations, you can see that there is a raise in the track elevation, which is obvious. What you should have is just before tamping and immediately after tamping. The purpose of tamping is to raise the rail, and one of the sites, actually Madison, you see there was a significant raise in the track elevation as you just before tamping is the black line and after tamping is the red line. And we did this on both rails just to see how. Analysis of acquired data, just so all the instrumentation were connected to a wayside box like this. So every time we need to acquire data, we just go and then we have our amplifier and analog to digital card and a laptop, and we just connect everything to the wayside box, and then we start acquiring data under train, as well as the permanent settlement. So this is just an example dynamic response. What you can see is as the train passes 1, 2, 3, 4, 5, all the MDDs will give you deflections, and you can see what is deflecting by. This is just an example. I'll go through the exact analysis. So let's just see how we can interpret the data. As I said, this is an independent anchoring system. So every LVDT, the voltage is the deflection of that layer. So if you see LVDT 1 showing some deflection, that is basically the ballast layer, because the LVDT 1 was always in the ballast layer. And similarly for different layers. And then positive voltage is layer settlement. Negative voltage can actually mean a lot of things. First thing, layer expansions, like somehow your layer is expanding, if it is expanding. Second is downward migration of the anchoring MDD. So basically, think about this, the core of the LVDT is free, right? The inductive coils are actually fixed to the side of the layer because they are clipped in. So if there is actually somehow the core is moving, which essentially means that the bottom LVDTs are moving downward somehow, like you lost grip or something, so it slipped. That means your core is actually moving in the negative direction. It can actually show you a pseudo expansion. And other one is polarity reverse during instrumentation, because it's doing it at the middle of the night where there is only 3.5 hours. There is a lot of potential for reversing the polarity, and we actually came across it twice or thrice, and we were able to fix it on the spot. How do you know if polarity is reversed? You collect dynamic data under a train. If when a train is passing, all your LVDTs should go down, like all the layers should go down. You should not have any expansion. But if under a train you see that some of the voltages are shooting up as negative, that means you're doing something wrong, and you just reverse the polarity at that point. And that's what we did. Duration. Now this MDD, so there are two types of data acquisition we did. One is when the train is going, which is what I call the dynamic data basically. Second is when we installed the MDDs, we got the zero position, the first day position of individual layers. And then if there is any permanent settlement going on, we just go in every 7 days and then take data from that point. So basically if the LVDT is permanently going down, that will give you a permanent settlement. So two types of data that I'm going to do. And again, because we are here, the instrumented site is in Pennsylvania. So again, Mr. Mike Thomas of Amtrak, he has been kind enough to go and collect a lot of data. I came back on the 10th of August, so anything after the 10th of August, actually all the data that he has collected. Of course, he has not collected any more dynamic data because it's kind of a two-person job. He just goes and collects a permanent settlement with time. We received just a couple of notes. We received a lot of rainfall 4 or 5 days immediately following the installation of sensors. We didn't lose any sensor or didn't introduce any unexpected noise in the data or anything, but just a comment. I mean, something may have happened in the layers or something, any behavior that can be, you can see that we got a lot of rain, and also we had a dry period, and then we had some rain also. But anyway, so let's just take a look at one of the data, and then others are similar. So this is the 15-foot location from North Abutment at one bridge approach, which is the Upland Street Bridge approach. These are the locations of the LVDTs in one MDD. So between 1 and 2, you have like about 19 inch of ballast. Now what is this 19 inch? This 19 inch is from the top of the tie. So the ballast layer thickness is probably somewhat around 12 inches because the ties are 7 inches deep basically. And then we at about 19 inches we hit an interface of clean ballast and fouled ballast. Now that may be either cleaned ballast that has been fouled, or that was maybe some kind of a sub ballast which actually is now fouled. So we pushed the third LVDT at the interface of the fouled ballast and the sandy loam. Now this is the thickest layer that we got, and then there is a thin sand layer we hit here, and then again sandy loam we got all the way down to the anchor. So this total is 118 inches, basically 3 meters. Okay, so if you induce any voltage in 1, that actually means how much this layer only settled. Then 2 is this layer, 3 is this layer, and so on. So if you look at the dynamic data, this is under one of the high-speed trains, you actually see that this is settlement in millimeters and time in second as the train is passing. Clearly, first thing you can see the effect of the 2 axles of a given rail car moving, and then there is a rest period, and then 2 axles moving. You see that, and at the top you actually have about 1.5 millimeters versus as you go down, this is only 0.162. Interesting thing is, see, this is a very thin layer of fouled ballast, and some of the times we actually saw that it actually had some kind of a pseudo binding material, like maybe from the disintegration of the ties or something, and it actually had a lower settlement than this LVDT3, which is the sandy loam. The sandy loam was actually settling more than the fouled ballast.
You mean deflection or something?
Deflection. These are elastic. Well, it may have elastic and plastic, both components. This is under the train, direct loading. The settlement will come later. And this is again 60 feet. And one thing you see is that at the 15-feet location, it's about 1.5 inch at the top, but at 60 feet, it's only about 0.32 inches. So actually, the 60-feet location showed less dynamic deformation under the road than anything. And this is again the layer profile. Let me quickly go to the settlement, the permanent settlement, and these are from the offsets, by the way. Like, this is not under a train. This is when you go at 7 days intervals and then you just collect. So this is number of days. This is in millimeters. This is the ballast. So the question when we started the instrumentation was that which layer is settling the most, which layer is contributing the most for your permanent differential movement. The clear answer, at least on these sites that we instrumented, is that the ballast is settling the most. Now that is actually one of the hypotheses we started with, because it is coming back so quickly after resurfacing that it has to be ballast, because if it cannot be the subgrade and then it will correct itself and then it will come back very quickly. The subgrade is, or that far down, it will probably not settle that fast. So you see it's about 5 millimeter versus the next one is the fouled ballast and then the rest. Now you see MDD3, it actually shows kind of potential expansion. I mean, the reason I'm showing this like this is that we were able to get very consistent data. I mean, there is no significant noise or something. So even if it is showing only 0.25 millimeters of deflection, it is what it is. I mean, it is not just an error in the data or anything. Something happened there. Maybe the MDD4 kind of slipped a little bit, or maybe it actually expanded. Somehow the sandy loam actually, there is maybe some kind of a dilation happening at that position and it actually went up a little bit. Again, this is permanent settlement at the other site at the 60 feet location, and you see that the ballast is still the maximum, but the magnitude is definitely a lot less. 4.5 millimeter versus only about 1.5 millimeter. So as you move down from the abutment, in this case, the settlement is also going down, and it was also reflected in the dynamic deflection under the data. Similar is the case for Madison Street Bridge, and what I want to, and this is again similar, I don't want to spend time on this. Here is what I want to show you. You see this, there is a jump. It was actually, without our knowledge, it was actually tamped after about 20 days. So when they tamped and raised the top, raised the tie and the profile, because the first MDD was within the tie, it was actually lifted up. So it actually showed up as a pseudo upward movement of that, of the location, and it was actually reflected because track 2 apparently was entirely tamped in that location. So at the 12 feet location, you see there is a lot of jump, but in the 60 feet there is still a jump, but not a lot. Maybe that is because the 12 feet is close to the bridge, so a lot more track profile error that they had to correct versus the 60 feet location where they did not have as much track error to correct. And this is again the dynamic data, and then oh, by the way, the Caldwell Street Bridge, the third bridge we instrumented, we actually instrumented, we didn't like offset. Like the first one, remember I said 10 feet and 60 feet from the bridge approach, or 15 feet and 60 feet. But this one was at 80 feet, and we instrumented both ends of the tie just to see how the differences are. And we actually got the same layer profile and deflections, and the trends are also very similar. So I see 8 feet west rail, you actually have this much, but actually on the east rail also slightly different. This is like 5.5. versus about 5, so 0.5 millimeter of difference. That is what we have. And from the wheel load data also, we were able to calculate from the strain gauge, you can actually get the wheel loads. And this is, I'm just showing one bridge approach, Upland Street Bridge. At 15 feet, it is about 27,500 pounds, by the way. And at the 60 feet, this is 29,000. It is just detecting a little bit of difference. Because this is the same wheel. I mean, remember this is upland, so it is the entrance to the bridge. So at 60 feet location, this wheel will come first, and then it will get closer to the bridge, and then this will come second. That is the first peak. Actually, it's measuring a little bit different, but you can still, when you want to correlate the MDD deflection data to the wheel load measurements, you can actually take the two together. And what I'm currently working on is putting all these into some kind of a track analysis software. Like one of the commonly ones used is like GeoTrack, and although it's not like a finite element based program or something, but what you can actually do is take the wheel loads, and you have the elastic deflections, so kind of back calculate, assign different modulus to the different layers, and kind of back calculate the modulus, and then that will go into our ultimate FLAC modeling to see how the different things will work. Last thing, because at least so far, we will keep monitoring this, by the way, over the next 1 year, so we will still keep going data. I'm actually going there next week to talk about some of the analysis with Mr. Mike Thomas, and then if possible, collect some more dynamic data. And he's been collecting some offset measurements, which is the permanent settlement. And at least so far, we think And we are pretty sure, at least from the deflection data, that the ballast is settling the most and contributing to the differential movement. So what can be the different remedial measures? There are sometimes you can just do geogrid reinforcement, and that is like one of our research partners, as I said, is Tensar, and we are thinking of like if Amtrak approves and if one of the sites there is their maintenance schedule and maintenance budget permits, then we will probably work with Tensar and at least suggest placing some geogrids, and we'll do first the analysis using our modeling work and see how we can improve the performance and eliminate the significant ballast movement. Another technology that people say is that because tamping actually degrades your ballast significantly, so there is something called stone blowing. You can actually just put kind of pea gravel, not pea gravel really, but kind of uniformly sized particles just below the tie instead of really pushing it really hard and degrading the tie potentially by tamping, what you do. And this is actually a location. Basically, you put kind of a tube right next to the tie where you think there is a gap, and then you just insert. So basically, you're lifting off the tie over there. And then glued ballast. This is something that Professor Tumler has been working on, and Hussein and Mike, and before that Marcus Durst, they did a lot of lab testing. And also in Europe, there is something called Zytrac that they use, is basically kind of putting some kind of a polyurethane and kind of gluing the ballast so that it becomes stiffer and it doesn't, right, acts as one body instead of like the free flowing, and the initial settlement of the ballast can also be avoided. I guess that's the time, so I'll just end here. Thanks a lot for your attention, and I'll be happy to take any questions that you may have.
I do have a question.
Yeah.
Can you elaborate a little bit more in the path that the wires of the SMT and the strain gauge follow from where they installed to that?
Yeah.
Tiny box?
And again, if I have like hundreds or thousands of photos from the installation, I can actually share some of that with you later. But let me just quickly go to that slide and. Oh wait a second, it was actually lower than that. Okay, so you see this track is actually for this particular location. This is actually track 4. Okay, so what we do is and this location was instrumented on track 3. Okay, so just the next track on the other side, what we did. So, for example, imagine you are installing this tie and this rail. Okay, so what you do is you go down into the ballast, and then you keep going. You dig a little bit, reach the bottom of the tie, and then you see the clips that are here on this tie. So you clip the hose with the tie so that it's not flowing freely or anything, and then you just keep going in the crib area under the rail, under the tie, and keep clamping them, and then take to the wayside box, and then you collect your data over there. This is, I mean, again, we greatly benefited from the Amtrak instrumentation group, Mike Thomas, Marty Perkins, and Carl Walker. They do this basically almost every day. So they taught us how to take this and protect this, and actually how you need to mark those particular ties with paint so that whenever there is a broom or a tamping machine comes, they know and they see that they're not supposed to do that. So all borrow from there.
Are these all tamped before the measurement?
Yeah, that's what I said. Like, first of all, we drilled, we put the bottom 3 ties, and then we put the tamping protector, and then we tamped.
So the deformations you're measuring are kind of expected.
Yes, not with time though.
Why? Don't they always have a slow speed warning on any track that's been tamped because the ballast isn't stable?
No, not really, because at least in this corridor there is no slow speed warning. What?
On freight railroad, that's true.
Yeah, freight railroads, yes, sometimes. But what they do is they have a dynamic track stabilizer that always goes with the tamper. So once you have tamped, there is this dynamic track stabilizer. It's nothing but a vibrating machine kind of thing, and it is basically vibrating the track and assuming that all the initial reorientation has taken place. So there is no slow order. It just goes directly on top of that. After that.
That was my initial thought, was a lot of that deformation was just due to the tamping. Because you're essentially dilating the ballast, it's going back to where it wants to go.
It is true, but for 60 days, It doesn't, right? I mean, but yes,
Slowing down.
but definitely, yes, it is definitely slowing down, and definitely one of the theories, and that is the reason one of the remedial measures that we have talked about is the stone blowing, is because tamping is actually you are fluffing off the ballast, and then it's of course going to settle. So you want to avoid that, and how do you do that is what's being discussed right now.
It almost seemed like, if that's the mechanism, then GeoGrid wouldn't work.
What our understanding is that not all of it is just because of the tamping fluff. It is basically after the tamping also your normal ballast is also like dilating or moving around and everything. So if you do that, you can capture that with your geogrids.
Okay. One last question. The wheel load that you showed, is that normal for Amtrak?
Yes, yes.
So 29,000 pound wheel loads?
Yeah, that's somewhat in that range. It is not as high as the freight loads, because freight loads is about somewhat around 36,000 pounds. Mike?
Yeah.
I think, yeah, 36 skip is the normal freight road, and these are high-speed trains. So
They do actually get some of those 36 skip loads. Well, I don't think that's the 36 skip or not, but
on SLS?
no, not themselves. That's the freight load.
Yeah, no, I'm talking. The wheel load I showed was for an Acela, so I think that is somewhat around 28,000 to 30,000 is normal.
So this is shared corridor, right?
Actually,
Not well. This is a shared corridor, but the track 2 and track 3 is predominantly, at least during the busy times, it is predominantly high speed trains, and sometimes if they can reroute, like they can route freight trains through that.
actually, Dad, to go back to your earlier comment about the wheel loads, actually the Acelas would be lighter. They're about 23 tons max axle load. The 28 is going to be the quote, I guess
The Philadelphia regional.
The regional trains.
The regional trains.
trains.
But I'm pretty sure what we measured was an Acela. Now, remember, I'm not distinguishing between the dynamic effect and the static wheel loads in this case. This is just train gauges, so it actually incorporates.
If it's dynamic, yeah, that makes
It
sense.
actually incorporates the dynamic also. So, but I'm pretty sure that the train I'm showing is Acela. So,
Yeah, that would make a lot of sense.
yeah.
So.
So,
Description, when you say dynamic, it is a description in the Facebook or?
it is just voltages measured from the strain gauges. So there is no. I'm not.
So it is not something that we add half of the.
No, I did not add anything. This is directly voltages measured from the strain gauges. That's it. Wheel loads.
How did you identify the interfaces? Is the material which were coming out
Yeah.
while you were putting
Yeah.
it?
So you can essentially say that there is a plus or minus 1 inch error always.
And how much was the variability in identifying the interface locations from one spot to the other spot?
On the Caldwell Street, which I just showed, the third bridge, Madison. So this is Caldwell. So this is the site where we instrumented both sides of the tie. So as you can see, it's actually pretty uniform. So ballast, foul ballast, brown silty sand, silty clay, and then you have ballast, foul ballast, and then we got something called possible HMA layer. Then there is plasticity clay and medium plasticity clay. We thought this was an HMA because when we were drilling, we kind of saw that it's kind of like when you drill through asphalt, whatever you get back, that is what we thought. But then it was only like about 1 inch thick, so I don't think that's really very critical. But if you are close to each other, the locations, there's not a lot of variability, but then otherwise there was some variability. And this is all visual classification, by the way, like during the drilling. This is not, we are currently working on getting the lab classification done. Anything else?
After you collected data from the MTVs, who was responsible for analyzing the data
Me.
and providing the differences?
Me? I was.
So how did you analyze the data? How did you, which frequency in terms of sampling out of those?
Sampling, we sampled at 2000 hertz. So every second we collected 2000 data points.
So is that like some typical frequency for sampling that they use? Or?
Well, yeah, apparently maybe Amtrak uses 2000 because I was suggested 2000 hertz by Mike Thomas, so I just used that. 1000. It's just a matter of how many data points you want per second. I don't think there is anything. And then you just take the calibration factor for the individual LVDTs and then corresponding millivolts to just relate that to millimeters. It's pretty simple.
Okay, oh, one last question.
You were talking about differential settlement or differential
Movement, yeah.
reflections, yeah, between the bridges and the track. So did you measure the movement of the bridge?
No, no. I think it is pretty safe to assume that there is no movement of the bridge. So, no. Yeah. So this, yeah, differential basically, yeah, it is just assumed that the bridge is not moving. However, that's a good question because one of the approaches, one of the alternatives that people have suggested to take care of some of this differential movement, especially under moving loads like under trains, is that, you know, there is something called open deck bridge versus ballasted deck bridge. So bridges sometimes do not have any ballast. The ties are directly placed on top of the bridge. Now that is a very stiff system. What they have suggested is that why don't you put some ballast just on top of the bridge, so that is actually kind of a shock absorbing mat, so that it actually, your track on the bridge actually settles by a little bit, and then you are also settling here, so you're bringing it closer. So there are two approaches. Either you reduce the settlement on the approach, or you slightly increase the settlement on the bridge, and then you match the two. So differentially you are just trying to avoid, that's it. But permanent settlement, as Hussain said, I hope the bridge is not settling.
Well, yeah, it's just that I think that 80 feet from the bridge is a lot.
It is a lot, and that is why I said, remember in the very beginning, I said there may be some dynamic aspects that are also coming into picture, like when the spring mass of the bogie is actually bouncing and when you are getting the peak load, that is actually when probably it is not immediately, definitely. I mean, you know, there is some inertia, it actually needs some time to completely like hit the dynamic as the peak load. That's what it is.
Okay, thanks, Deb.
Thank you.